So today we're going to talk about balancing equations, but I'm going to talk about the test first. I think I was moderately pleased with it. Yes, moderately. Yes. I mean, it's always a mixed bag, right? So let me look at some of the numbers. Now I'll post the grades after this when I get up to my office. But yeah, so you want me to wait? Okay. So this is the averages by absences and letter grades. So I was trying to track. We haven't had a lot of class periods. So we haven't had a chance for a lot of absences, but it definitely shows a huge trend in terms of absences. And so obviously the attendance grade, you have up to 3 absences, and so there's not, even if you've had 3 absences, you still have 100 for attendance. Okay, but there's some people that have missed a lot, and so their attendance grade's dropping off. But on average, like the people in the A group, B group, C group, and so on, these are the average number of absences. So, and so like an average doesn't, it's like how you come to half a class. The average is always weird when you're talking about counting things, but on average, half an absence, right? Some people had 1 absence, some people had 0. But then look at the homework average. It's not that the absences cause a poor performance on homework, but it's what they call correlated. So correlated is not, you've heard the phrase, correlation is not causation, right? So missing class doesn't cause you to do poorly on homework, but missing class and doing poorly on homework are correlated. Meaning if you're not engaged in the course by coming, you're also not engaged in the course by doing the homework, right? So it's correlated through that person. So this is the sort of the correlation between homework average and absences. This is the correlation between exam average and absences, and this is the correlation between weighted average. So your grade is actually based on this column, and this column is calculated according to the syllabus, right? So homework is 35%, so I take your homework average multiplied by 0.35 and add it to your attendance average multiplied by 0.05 and your exam average multiplied by 0.4. And you say, but that only adds up to 80. And yes, at the end of the course, the lab average will come in, and that'll be 0.2, 20%. Okay, so that's how I'm calculating the weighted average. I don't have your lab grades. I won't have them till the end. Okay, so I'm just calculating 80% of your grade and dividing by 80%. So, if you've got fully 80% of everything, then you have 100 in the lecture. So that's what's going on. Yes?
Are we going to be able to, or when could we get our tests back so we could try to see what we got wrong?
Yeah, so it would take pretty much a whole lecture, pass them out and take them back up and everything. So come by my office. We can, in the afternoons, I'm there. Try to, find me, text me or call me, I would say, or email me and tell me when you're coming. Come by as a group, if you have a study group, I'll come by and I'll pass them out to you. Yes?
I know you said that we'll get results probably after this class.
Yes.
But will we get the physical paper back to see what we missed?
You'll need to come by and look at it. Yeah. Okay. So how many are in each letter grade? Well, this is surprisingly even. I did not do anything to make this the case. Like a lot of times people think the professors try to make it be, so many F's and so many A's and all of that. These are the cutoffs. I did this totally numerically. So based on the weighted average, if you were above an 89.5, you had an A, 79.5, B, and so on. So these were the grade cutoffs, and this is the number of folks in each group. Okay. And then this is that correlation that I was talking about. I know you probably can't even see these numbers, but I was shocked at how strongly they were correlated to attendance. Look at homework average. 98% of the change in homework grades correlates with attendance. So again, it's picking up on something. Again, and 94% of the weighted average. Now, the Alex progress for the Chapter 3 homework A that's due tonight, I'm so happy. Look how many people have already started it. I told y'all, keep grinding. I know you just finished an exam, get started. So a lot of people on Saturday got in there and started doing the homework that's due tonight. So good job, you folks. The 16 who haven't, get on it today. It's not that hard, but they are going to get more difficult and take more time. So you definitely want to get ahead of things. So let's jump in. These are the topics that are due tonight. It is a lot of topics, but it's all balancing equations. There's a little bit on mass percent. So before we get into balancing the reactions, let's just think about chemical reactions. Now we haven't covered what Gibbs energy is, but I want to at least introduce the term. So think about a ball on a hill. When we have a ball on top of a hill, we call it potential energy. And when it rolls downhill, it converts the potential energy into kinetic energy. It reaches the bottom of the hill, it's gotten rid of that kinetic energy, and now it has lower potential energy. So this concept of potential energy, you know, right? If you're standing on top of a tall building, you've got a lot of potential energy. And we would call you, if you were a chemical, we would call you reactive. So chemicals that have a high potential are very reactive, and they go downhill. So this idea of energy being on a hill is a good idea. So keep that idea. Hydrogen and oxygen are very reactive. They're pretty far up on a hill. And if you get them over the barrier, they'll form water. Okay. And so water's downhill from hydrogen and oxygen. And so this is what we mean by a chemical reaction. Those chemicals are reacting, making a substance that's downhill. So this reaction is spontaneous, and this is a combination reaction. So part of today's lecture and tonight's homework is classifying reactions. And so a combination reaction is one of the types of reactions, and that's one of the blanks on your page. Okay. So this is a combination reaction because two molecules are combining to form a new molecule. So hydrogen and oxygen combine to form water. Okay. We could run this backwards. We could run it uphill if we provided energy to it. So we could put a battery in water and you could see bubbles, and those bubbles would be hydrogen and oxygen coming off the battery. That's kind of fun to do if you want to demonstrate that. Put a 9-volt battery in salt water and with soap, and it'll make bubbles, and then the bubbles pop when you light them with a match. Be careful. Okay. Don't do this at home. I have to say that. This, what's happening here with water, it's coming apart, it's decomposing. So this is a decomposition reaction. So that would be another, so if you take a molecule and it breaks into smaller parts, it's decomposing, that's a decomposition reaction. Not all decomposition reactions are uphill, but this one is. Okay. Now this hill, this Gibbs energy, that Gibbs energy is what we call chemical potential. So just like we have potential energy against gravity, with elevation being the main number that we would use, Gibbs energy would be the number we would use for chemical reactions. So chemical potential is the Gibbs energy. Notice we can write reactions forward and backwards. Okay? And the energies are, they make sense, right? If hydrogen and oxygen are uphill from water, if I write it forwards like that as the combination reaction, it goes downhill. If I write it in reverse, it goes uphill. But you can write the reactions forwards and backwards. That just might mean different things in terms of energetics. It might be a spontaneous reaction if it goes downhill, a non-spontaneous reaction if it goes uphill. So spontaneity is a new concept too. Again, not on this section of the course, but I'm introducing this idea. Balls roll downhill spontaneously. Once you get it moving, you don't have to continue fiddling with it. It'll just do its thing. Same with chemistry. Once we get oxygen and hydrogen to start to react, we don't have to touch it. It goes downhill spontaneously. Whereas going uphill, not spontaneous. We have to constantly provide electricity, as an example, for that reaction to go uphill. So we're having to put energy in to make it go uphill. That's not spontaneous. Spontaneous is you don't have to do anything and it'll just go. Okay, so these are the different types of reactions. We talked about the combination reaction and the decomposition reaction. And then now we have some different substitutions. So a single replacement reaction. So this is an example where you have an acid reaction where that proton is interacting with lithium and it's taking electrons off of lithium and making lithium chloride, salt, and hydrogen gas. So the proton's grabbing a couple of electrons and making hydrogen gas. And since we're replacing the hydrogen with lithium in this compound here, that's a single replacement. So we're just replacing one element. What does it mean replacement? Well, this has a relationship with chloride, and we're just changing a partner. So we're just replacing one partner. Okay? And then this would be a double replacement. So here we have a relationship, if you will, of silver and nitrate and sodium chloride, and then just swapping places. So we're replacing the sodium on the chloride with the silver, and we're replacing the silver on the nitrate with sodium. So that's a double replacement. And those are the 4 types of chemical reactions that you're going to be classifying today. The other one we'll add is combustion. We'll talk about combustion reactions, and that's a fuel plus oxygen making CO2 and water. Any questions on these? My question is, how do we know a reaction happened? So when we mix 2 things, like a silver nitrate and sodium chloride, if we mix those together in a beaker, they're both colorless solutions. They're salt water, okay? Silver nitrate and sodium chloride are salty water. And we mix them together, and all of a sudden we see a white powder come out, a precipitate. And so this is one way that we see things. We see phase changes, like gas, liquid. Aqueous is a new phase for you, perhaps. It just means an aqueous solution, a water-based solution, and solid. But we might see a color change too. We might see temperature changes. So even sometimes when we have a reaction between aqueous solutions, maybe an acid-base reaction, we don't see a color change, we don't see bubbles, but we feel heat. We're like, oh, something must have happened. A chemical reaction has happened because we see heat coming out of that solution. Or very rare situations, we see cold. But a lot of those produce bubbles, and so there'll be gas given off, and the reaction will get really cold. It'll be an endothermic reaction. Those are fun. So this is, again, this combination reaction that we showed before. The reason we know that something happened was there's a phase change. So we need to include that phase information. So we need to show that hydrogen's a gas, and that oxygen is a gas, and then it's forming the liquid water. This is, I don't know if y'all even remember any of the space shuttle launches, but the big tank on the space shuttle was hydrogen and oxygen, and they combined in the shuttle engines to produce water. So this reaction was what drove 65 to 75% of the thrust for the space shuttle to get it into space was this reaction. And the big white billowy cloud was the water. So it formed a lot of steam coming out of the back of that engine, and you saw this big white cloud coming out. Okay, decomposition reaction. Here we're going from liquid water to gaseous CO2 and oxygen. Again, if you have salt water in there, the salt just helps it conduct electricity. But if you drop a 9-volt battery into a glass of water, you'll see the bubbles form at each of the poles. One of those would be hydrogen, the other pole would be oxygen. Okay, for the single replacement reaction. Again, how would you know it happened? Well, that H2 that's formed is a gas. And so if you drop lithium solid, lithium metal, into hydrochloric acid, which again, this is an aqueous solution of hydrochloric acid, then you get lithium chloride, also an aqueous solution. So you really can't tell the difference in the aqueous solution between HCl and LiCl. They're both aqueous. Neither one of those is colored. And so you wouldn't be able to tell that there was a reaction from the aqueous pieces unless there's a color change. But you see the solid dissolve, it goes away, and you see gas produced. So the change in phase is what tells you, hey, there's a reaction going on. Okay. And then the double replacement. Here we have 3 aqueous pieces in a solid. So you mix this clear solution of silver nitrate and this clear solution of sodium chloride, and a precipitate forms. So you see this white powdery solid form in solution. It gets cloudy and then it settles down. You've got a white powder in the bottom of the beaker. And then the liquid above it is sodium nitrate, aqueous, also colorless. So we can't tell anything's happened from the aqueous pieces, but we can definitely see that something's happened when we form a precipitate. So this solid forms, it's a product, so we know the reaction went forward and did something new, so we know there was a chemical reaction. How do we know that this will be a solid? Well, that's going to be in a future set of homeworks. So there's solubility rules. So some things are soluble, other things are not. Okay. So if we mix sodium chloride and potassium nitrate, we would just have salty water. There would be no reaction because they're all going to be soluble. So we have aqueous everything, and there wouldn't be a color change, there wouldn't be a phase change, there wouldn't be anything. So there'd be no change except we diluted both of them by putting them in a larger volume. So there's no chemical reaction there. So this precipitate is a big deal. So this is a double replacement reaction, but some people might call it also a precipitation reaction. So they might classify that as a precipitation reaction. Now we get into balancing chemical equations. The reason we say the equations have to be balanced is because of the law of conservation of mass. So if I'm mixing beakers of solutions, I don't expect to lose large amounts of material. I mean, I might lose something with evaporation, but let's take evaporation off the table and spilling off the table. If I start with 2 pounds of stuff and I mix them together, I ought to have 4 pounds of stuff. Right, and so we're not, annihilating matter and turning it into energy and so on. We're just doing chemical reactions, and so we shouldn't lose any mass. And so if I start with 3 atoms of oxygen, I'm going to end up with 3 atoms of oxygen. Okay, and so hydrogen and oxygen combine to make water, but there's a problem. Naturally, hydrogen and oxygen come out in pairs. So if we look at that reaction, I've lost something. What have I lost? I've lost a whole atom of oxygen, and we can't do that. Okay? That would, just to annihilate a whole atom of oxygen would be like a nuclear reaction. I mean, there would be a lot of energy coming out of that if it truly did disappear and turn into energy. Okay, Einstein's equation equals mc squared. It would be the mass that we lost turned into energy by multiplying by the speed of light. It'd be an enormous amount of energy. So what we're going to do is we're going to put a 2 in front of there to make sure I have 2 oxygens. But that screws up the number of hydrogens. So then I got to put a 2 on the other side. Okay? So we need more hydrogen atoms, and so I'll put a 2 over here. Now everything balances. Okay? I've got 4 hydrogens, and there's 4 hydrogens over here, 2 oxygens, and 2 times the whole molecule gives me 2 oxygens. So SpongeBob's happy. It's balanced, okay? So this is how you balance an equation. Number and types of atoms, just go back and forth, and some are easier than others. And so there's a whole category in ALEKS of ones where the coefficients don't interfere with each other, and then there's a category that's like level 2, where they do interfere with each other. So you've got 2 types of ALEKS problems on balancing equations. So here's level 1. Okay, so I've just got them in rows here. So up there, this is a combustion reaction. So the way I do this is I start with that reaction, and I start with the carbons. Always save your hydrogens and oxygens for last. So start here on the carbon. And I come over here and I see that there's 1 carbon on either side. So that's great. And then I look at the hydrogens. So I have 4 hydrogens on the left. Over here they come in pairs, and so I've got 2 times 2. Okay, so this is 4 hydrogens. And then I look over here and see I've got oxygen there and an oxygen there. So I've got 2 oxygens here, and it always looks like 20, but that's 2 oxygens. Okay, and 2 oxygens here. So that's a total of 4. And so they come in pairs, and so 2 times 2 gives me 4. So that's great. I got 1 carbon, 4 hydrogens, 4 oxygens on the left, 1 carbon, 4 hydrogens, 4 oxygens on the right. if I've got the same number and types of elements, then what does this reaction actually do? This is what we mean by chemical reaction. So all they're doing is changing the bonds. Does this reaction go forward spontaneously? From your life experience, can you tell me if this reaction goes forward without any extra help? What is CH4? Methane, and where is methane found? Like if you have a gas stove or a Bunsen burner in the lab, what do you have to do to get that thing started? Just provide a little spark, and then you don't have to do anything. All the reaction takes place. It's an oxygen atmosphere. You just have to have a little mixing, and the mixing is that little thing on the bottom of the Bunsen burner. You adjust that little screw, and it allows oxygen in at the right rate and mixes it, but it's spontaneous. You don't have to touch it after you get it started. As long as you supply the fuel and you have the oxygen and they mix and you have a heat to get it started, then it's self-propagating, it's spontaneous. So that top reaction is spontaneous, and the only thing that's happening is we're just changing what the atoms are bonded to. So because it's spontaneous, we know the products are downhill chemically from the reactants. So the methane and oxygen are uphill, the CO2 and water are downhill, and it's a spontaneous reaction going forward. Okay. So that's all we're doing, and it's all in the electrons. It's the electron cloud reaching out and going from carbon with electrons touching the hydrogens. It says, I'd really rather have oxygen, so it grabs the oxygens. And the hydrogens get together with oxygen. And so everybody's reacting with oxygen. Oxygen's a very reactive molecule. Okay, so let's level up. Let's do one with interfering coefficients. So we're going to start out with this, and this is methanol. And right away, you can know that this is a sort of a level 2 type reaction, because I've got oxygen here in the fuel and oxygen here. So I'm putting little sunglasses or glasses there, right? Pay attention. When you have oxygen already in the fuel, you know you got a tricky one. Okay? So we'll see why that's tricky. So start with carbon. So we've got one carbon on either side. Add up the hydrogens. Oh, this is a copy-paste error. Sorry. This should be a 3. So we have 4 hydrogens on the left. They come in pairs with the water, so I have 4 hydrogens on the right. And then when I'm looking at the oxygens, again, change that 4 to a 3. That's crazy. It's easy to paste those reactions down and then just change the numbers, but you got to change all the numbers, and I screwed that up. Okay, CH3OH. Now I'm looking at the oxygens. Here I've got 2 oxygens. Here I've got 2 oxygens. So I've got 4 oxygens on the right. And it's easy to make a mistake by trying to put a 2 in front of this, but not seeing this other oxygen over here. So what I have is I've got 1 already over here, and I need 3 out of this. So how do you get 3 out of 2? 3 halves, right? So I take 3 of those molecules, divide it by 2, and I end up with 3 oxygens. That's pretty ugly, and we don't like fractions in our coefficients. You notice up here it says whole number stoichiometric coefficients. I mean, is this reaction balanced? It is technically, but we want whole numbers for those coefficients. So how do I get rid of this 3 halves? I multiply the whole thing by 2. So everything in that reaction is going to be multiplied by 2. So I have 2 methanols with the, I'm going to change that 4 to a 3. Okay, 2 methanols, 3 oxygens, 2 CO2s, and 4 waters. And notice that 3 prevents me from dividing everything by 2. Like if I ended up with everything being a multiple of 2, I could divide everything by that, but I can't divide that 3 by 2 and get a whole number. Sometimes if you're working this and you sort of, what I say, get wrapped around the axle and you like keep changing all the numbers. You end up with everything balanced, but it's like 4, 2, and 2 and 4. You can divide everything by 2 and go to 2, 1, 1, and 2. Okay, but I can't do that with this one because of that 3. I can't divide by any single number and get whole numbers again. So that's balanced. They call this interfering coefficients because of this oxygen is in 2 places, and so you've got to figure out how to adapt to that. Surely there's a question on this one. Yes. Yeah. Yeah. So if you want to think about it this way, I've got an oxygen molecule, and if I divide that by 2, okay, it kind of breaks it into 1. So I end up with just a single oxygen atom, and I want 3 oxygen atoms. So if I multiply this whole thing by 3, I would end up with 3 oxygen atoms, and that's what I need. I need 3 oxygen atoms right here, and I need an oxygen atom right here to get 4 oxygens, because on the right I have 4 oxygens. So I'm looking on the right first, and I figure out how many oxygens do I need, okay? And then over on the left, I've already got one in the methanol, and so I only have 3 left to get, and they come in pairs. So I need to, the 1/2 breaks those pairs, and I need 3. So it'd always be 3. Let's say I needed 5, it'd be 5 halves. If I had needed 7, it'd be 7 halves. Yeah, so that's the way it is. If it's an even number, then I don't have to divide by 2 because they come in pairs. So if I needed 6, that'd be 3 pairs. But if I needed 5, then I got a problem. So it's going to be 5 halves, and then I multiply everything by 2. Yes. Okay, great. Yeah. Sometimes you get lucky and it's an even number, but not always. And so the interfering coefficients on Alex, I mean, it's going to give you ones that interfere. So again, so that's the level 2 ones. Do the level 1s, get real comfortable with it, and then you can start working on the level 2s. There's my total. Okay. So after I doubled everything, then I don't have 4 oxygens, I've got 8. And I've got 8 hydrogens, and I've got 2 carbons, and so on. Oops. Okay. Okay, so when we get into sort of measuring chemical reactions, these reactions are happening at the atomic level. Okay? That's really difficult to measure. In fact, even we do this all the time too. So if you go to the hardware store and you want to buy a little, let's say you're going to buy some deck screws, okay? You don't count them out. Or if you're going to buy nails, you don't count them out. What do? You buy them by the weight. Buy a pound of screws, okay? And there's going to be a certain number in a pound. So we weigh out small things by weighing them, okay? So same thing with atoms. We're not going to count individual atoms. 2 molecules of hydrogen react with 1 molecule of oxygen to produce 2 molecules of water. This is the masses that are involved in that. So 2 molecules of hydrogen is 6 times 10 to the minus 24 grams. 0.0000 go out, 23 zeros and a 6. That's really small. Plus the really small amount of oxygen, 5.3 times 10 to the 23rd oxygen atoms. And that'll produce a really small amount of water, 6 times 10 to the 23rd grams of water. So these are way too small for us to measure. Like even eggs, we don't buy a single egg, we buy a dozen eggs. And so we could use this word dozen, but a dozen is only 12. That's still way too small for us to use. And so we've defined this term mole. A mole is defined as exactly 6.02214,076. So that's the full number for a mole times 10 to the 23rd things. So I don't let this idea of a mole be confusing to you. It's like a dozen, only bigger. It's a certain number, just like 12 is a dozen. This is a mole. And that's a measurable amount, right? If I multiply these numbers by 10 to the 23rd, see here, 10 to the 23rd, then I'm into numbers that make sense, like 6 grams of oxygen or 5 grams of this or 12 grams of that. So this 6 times 10 to the 23rd gets it up into the measurable range where we can use our regular lab equipment. So let's do it in terms of moles. 2 moles of hydrogen reacts with 1 mole of oxygen to produce 2 moles of water. And so that's 4 grams of H2 plus 32 grams of O2 that produces 36 grams of water. Man, that's fantastic. That's easy to measure in the lab. And yeah, we're dealing with a whole bunch of molecules, but that's perfect. All of the 10 to the X's are gone. We don't have 10 to the minus whatever. And so it is perfect. So we need to learn how to convert mass to moles. And so that's a whole section of Alex problems too. So calculating and using the molar mass of elements. So in this case, the chemist weighs out 45 grams of water. How many moles of water did she weigh out? Be sure your answer has the correct number of significant digits. Okay, so water is made of 2 hydrogens and 1 oxygen. So we use the molar masses off the periodic table. So hydrogen, 1.01, I put 1.00. And then the oxygen is 16. So we add those together. 2 plus 16 is 18. So water is 18 grams per mole. Now, how many moles is in 45 grams of water? 45 grams of water. We're going to take that molar mass of water and we're going to use it upside down. Because again, if we want to go to moles, we need to get out of grams. And so the grams will cancel. So we use that molar mass upside down, where the grams have canceled. And we end up with the number of moles. So 2.5 moles of water. Two significant figures because that's what was given in the problem of 45. Okay. Any questions on this? Now the formulas that I'm sure Alex is going to give you is going to be super complicated, right? There's going to be parentheses and everything, so just work your way through. If you've got like just say, let's do something like, oh gosh, let me think of calcium nitrate, right? So that's 3 oxygens there times 2, so that's 6 oxygens. So it would be 6 oxygens, okay? And so that's going to be 6 times 16 grams per mole for the oxygen mass. And then you're going to add in 2 nitrogen masses. So that'd be 14 times 2, and then plus the calcium mass. So the parentheses, you just got to know that that's multiplied. 3 times 2 for the oxygens because of the parentheses. Okay, your question.
So how do you know where to round the weight of the actual element?
Yeah, I just put in 1 instead of 1.01, so that was actually a mistake. I should have put 1.01. But I looked up there and I saw that it had 45 grams of water. I knew that it had 2 significant figures, and so I could use the masses to 3 and be okay. Yeah. So as long as you have one more, because some of these are really long. Look at rhodium here, 102.90550. That's a pretty well-known mass. That's 7, 6, 7, 8. That's 8 significant figures for the mass of rhodium. So I don't know why that one's so well determined. I know why technetium is only 2 significant figures and in parentheses, because it's radioactive and it has like a 12-hour half-life. So it's not around long enough for you to get a good mass because it's falling apart all the time. Now perhaps your parent, but probably your grandparent, many of your grandparents have had technetium injected into their bloodstream. Yeah. Why would they do that? Anybody know? It's radioactive. It's crazy. Why would they put radioactive element in your body? Huh? No, it's actually to detect a sickness. And they do that. It's a radioactive stress test. And so it's in your bloodstream and it's emitting light because it's radioactive. And they can image your coronary arteries and see if they're blocked. And so your heart's pumping along and the radioactivity is coming around this side of the heart, and they can screen that and they can see that basically your arteries are glowing because they're radioactive. Yeah. And so I discovered this one time. I was getting ready for the nuclear chapter in Chem 2, 1412. And I had a Geiger counter and I had uranium acetate on my desk, and I'm trying to measure the radioactivity. And a colleague of mine came in the door of my office, and my meter goes, it starts making noise. And I was like, and I turned it towards him, and it got even bigger. And I said, Dr. Colette, are you radioactive? And he goes, today I am. And I said, why? And he said, I had a stress test with technetium, and he came closer and it pegged the needle. And I said, well, what's the half-life? We looked it up, and it was 12 hours or something like that. And I said, well, you'll still be radioactive in the morning. Will you come to my class? So he did, yeah. So I had the uranium acetate, was uranium. Everybody knows uranium is radioactive. I said, class, which is more radioactive, Dr. Colette or uranium acetate? And everybody's like, uranium. So we measured it, barely moved. And then we went over to him, and the needle peg, And now the students were like, why is he radioactive? So that's why, yeah. So they don't always do it radioactively. Sometimes they do other ways, but that's one of the options. So we got on that path because of the significant figures for the mass. So technetium only 2, but rhodium is like it's 8. Okay, so yes. Now,
Going off of that, they also do a radioactive iodine.
yes, and your thyroid will absorb the iodine. So iodine 131, yeah, and so it'll glow, and they can image it really well. Yeah.
And if you have like any like cancers relating to thyroid,
Yeah.
you'll be able to detect it.
And it has like an 8-day half-life. So you can take,
You have to
yeah.
stay isolated for a week.
Yeah, that's right. That's right. So it's crazy. Yeah. So, and then they have positron emission tomography. But y'all take PChem and then you'll know all about that. So it's a commercial for my senior level class. That's right. Unsolicited. Yes. Okay. So how many molecules of H2O are present in 2.5 moles of water? And like in the 2.5 moles of water, how many molecules are present? So you've got this 2.5 moles of water, which is 45 grams of water. How many molecules? 1 million? Say higher if you think it's higher. Higher than 1 million? Yeah. Billion? How about higher than 1 trillion? So that'd be 10 to the 12 times 10 to the 12. Well, this is it. I mean, what does that mole mean, right? A mole is 6 times 10 to the 23rd molecules. So 2.5 moles times Avogadro's number, that's what that number is, this definition of a mole, is 1.5 times 10 to the 24th water molecules. Absolutely enormous number. Okay? So then each one of those molecules has three atoms. And so you could take that many molecules times 3 atoms for every water. And it's this many atoms. 4.5 times 10 to the 24th atoms. So this is to show you that that's how many zeros, right? This is telling you how many zeros there are. So it's this many atoms. So, or if you put a 15 there, 1.5, then it's that many water molecules. So the atoms are small. They don't weigh a lot at all. And so whenever we're weighing out 2.5 grams or 45 grams of something, we're just enormous amounts of atoms, gobs and gobs. That's the official term. So.
Wait, how does the molecules, how did it change from 10 to the 23rd?
Oh, so just by multiplying the 2.5 times the 6, we got another 0.
Oh.
Yeah, and so then it went up to 24. Yeah. Yeah. So it would have been like 15 times 10 to the 23rd.
Okay.
Yeah, so but you could write the 15 as a 1.5 times 10, and so then that times 10 gets added into the 10 to the 23rd, and then you get 10 to the 24th. So that's a good question. And so that it can be like your brain can kind of break when you're using scientific notation like that. Yes.
So just to clarify, water, that's 3 atoms,
Mhm.
and then the molecule, I guess what's the difference vocabulary wise?
Yeah.
Like how in the military you would have like your platoon and then the
Yeah,
battalion and
yeah,
then the whole.
yeah.
What is that with like atoms and molecules?
Okay, so yeah, the atoms are the smallest unit, and then they make the molecules. Okay, you could have moles. Moles just a counting number. You could have moles of atoms. You could have moles of molecules. You could have moles of automobiles, planets. You know, you could have moles of anything. But in terms of the hierarchy, like you're saying, atoms are the smallest, then molecules. Yeah, and the molecule and a compound are the same thing. Yeah. I might hedge on that a little bit, because an ionic compound is not necessarily a molecule. Yeah. So.
One without metal.
Yeah. Yeah. So, like sodium chloride is a compound, but it's not like a molecule where the sodium has got a single bond to a chlorine. It's a sodium ion and a chloride ion, and so it's a compound, but it's not a molecule. It's an ionic compound. Okay, so then we can take this formula mass and convert it to mass percent, because a lot of times we want a certain amount of a substance, and we're only interested in, say, the hydrogen, or we're only interested in the oxygen, but we look at the shelf and all we see is water. It's like, well, water has oxygen in it, so I'll take that. What percent oxygen am I getting, or what percent hydrogen am I getting in that compound? So the molar mass of water, again, is 18 grams per mole. And the percent, you guys remember this just in general, right? Percent is part over whole, as a general definition. If I'm calculating the percent of something, then it's a part over whole idea. So we need to decide, if we're calculating a percent, what's the part and what's the whole? Well, the whole is going to be the molar mass of the whole molecule. So in water, 18 grams is the whole of the molecule. That's the mass of the whole molecule. All right? But then the part, if we're doing the percent of hydrogen, then the part is just the hydrogen part. So each hydrogen is 1 gram. So if I have 2 of those, then it's going to be 2 grams. So 2 grams of hydrogen over 18 grams for the whole water molecule would give us the percentage of hydrogen. Then you multiply that by a percent, and you get 11% hydrogen. So that's in a chunk of, say I have 100 grams of water, that's going to be 11 grams of hydrogen. And I could take 1 minus that and get the oxygen, since there's only 2 components, there's oxygen and hydrogen. But if there's 3 or more, then you can't easily do the 1 minus thing. So the oxygen, again, the part is just the oxygen part, 16 grams for 1 atom of oxygen over there, or 1 mole of oxygen over 18 grams for 1 mole of water, times 100%, and you're going to get 89. So 89% oxygen. This is a real simple example. Alex is probably going to throw a bunch of different compounds at you that are a little more tricky, but it's the same concept. When it says, let's say, potassium dichromate, if you want to know the percent chromium, you just, the 2 chromiums divided by the molar mass of the whole thing times 100%, and that's how you do it. You could do the 1 minus thing, you could check your work. All of these have to add up to 100%. So if you did every component in the molecular formula, then you could add them all up, and they should be able to check to add to 100. So 11% and 89% add up to 100%.
So when we got our molar mass, it was grams over moles, but when we're calculating our percentage, why does the moles not?
It's 2 reasons. One, it was too busy. Okay. The other thing too is if I put a per mole on the bottom and a per mole on the bottom here, the per moles are all gone.
Oh.
Yeah, and so it would have like 16 grams per mole of oxygen divided by 18 grams per mole of water. And so even
Just like an
mathematically,
understood thing.
Yeah, it's an understood thing, but also even if I put them in there, they would all cancel. Yeah, in fact, the grams cancel. So the percents are unitless because all the grams, it's grams over grams, and so the grams are all gone. Now this is all done by mass percent. When we get later on to volumes, like milliliters of this and milliliters of that, we could have milliliters on top and milliliters on bottom, and it would be a volume percent. So sometimes we need to distinguish whether we did the percentage with masses or whether we did the percentage with volumes. And they're going to be different if the substance doesn't have the density of water. Water is 1 gram is 1 mil. So water is unique in that the percent by mass or percent by volume are the same. But for other substances with different densities, it really matters whether you're doing the percent by volume or the percent by mass. But that's not today. Today's just mass percent. So I think we're done. Yes.
Sorry. So when we're using Avogadro's number,
Yes.
would you like us just like to go to 6.022?
Yeah, that's all I use. Yeah, I used to use the 4, but I put all of them in there so you know that there's more to it. So that went in the numbers straight off the National Institute of Science and Technology's standards page. But the 6.022 is 4 significant figures, and that's plenty. Yeah.
Yeah.
Great.